All right, so in the previous section, we talked about how we can use sequence models to help handle RL with partial observability. In the next section, we're going to go the other way and we're going to discuss how RL can help us train better sequence models, specifically for modeling language. And in the third portion of the lecture, we'll actually put these together and we'll have both partial observability and language models. Okay, so what are language models and why should we care about them? Well, a language model at its basic level is a model that predicts next tokens. You can roughly think of tokens as words, although in reality they're not words, they're more like combinations of characters. It's actually a little complex as to what a token is, but roughly speaking, it's some granular representation of natural language. Typically, we use transformers for language models, and the way this works is we take our sequence of tokens, x0, x1, x2, x3. At every position, we have a little encoder that encodes discrete tokens into a continuous space, along with an encoding of their place in the sequence. Basically, their place in the sequence is an integer, 0, 1, 2, 3, 4, and those are encoded into a continuous representation, which is then passed to what is called a masked self-attention layer, which is essentially a transformer that can produce a representation at each position conditioned on representations at previous time steps. That's what the masking refers to. Those are then transformed with some per position nonlinear transformations, and this self-attention block is repeated some number of times. And that's essentially what a transformer is. And then at the end, at every position, we read out a distribution over the token to predict, which is basically just a softmax. And then we predict the next token. So at the first time step, we read in x0 and p0, and then we make a prediction about x1. And if we're decoding, then, for example, we would start off with some token like the word I. We decode some word like. That word is then used as the conditioning information for the second time step. You make a prediction about the next one. I like POMDP solvers. And there you get a decoding, and at the end, the model outputs an end of sequence token to indicate that it's done generating this particular generation. So that's basically a transformer language model. Now, for the purpose of this course, you don't really need to know anything about how the transformer works, so you could simplify this diagram to essentially be some kind of box, which we call a transformer, that sequentially reads in tokens and predicts next tokens. So at every time step, it's modeling the distribution P of xt given x1 through t minus 1. And by repeatedly sampling from that distribution, you end up with a sentence like, I like POMDP solvers. Notice that this model is not Markovian, so every token depends on all previous tokens. Of course, the widely known ChatGPT system, Bard, Claude, all of these things are examples of language models. And deep down inside, what all of these systems are doing is generating language token by token, where you specify the tokens for the prompt, and then it generates the tokens for the response. Now, language models are typically trained with supervised learning, in the sense that you give them lots and lots of English text, or text in other languages, and then you have them use all of that data to predict the next token given all the previous tokens. But we can also train them with RL if what we want is not to match the distribution in the data. That is, we don't just want them to output the same kind of text that we saw in the training data, but rather we want them to maximize some reward function. And that can be extremely desirable in many settings. Why? Well, for example, you could use RL to get language models to satisfy human preferences, to produce the kind of text that people like to see. You can also use RL to get language models to learn how to use tools, to learn how to call into databases or calculators. You can also use it to train language models that are better at holding dialogues with humans and achieve dialogue goals. And we'll actually discuss all of these. And these are all different than simply matching the training data. These are all things that require RL rather than just supervised learning. Okay, but in order to be able to apply RL to language models, we do have to answer some questions. What is the MDP or POMDP that corresponds to the language generation task? An MDP is determined by states, actions, rewards, and transition probabilities, and we have to choose what these things are for our language generation task. Now, there's some obvious intuition, like, if you're generating language tokens, probably your actions have something to do with language tokens. And if your goal is to maximize user preferences, then your rewards probably have something to do with user preferences. But actually getting those details right has a few interesting design decisions. So what is the reward? And also what algorithms should we use, right? So we learned in the previous section that certain algorithms handle partial observability. Some of them are, in previous lectures we saw some of them are good for off policy, some are good for on policy. So we have to make some choices. So let's talk about some of those choices. And we'll start with RL training of language models for what are sometimes referred to as single-step problems, which is the most widely used application of RL for language models. That's how ChatGPT, for example, is trained. And then in the next section, we'll talk about multi-step problems. Okay, so here's a basic formulation. We have some prompt. Maybe the prompt is like, what is the capital of France? And the transformer makes predictions. Now, it's not actually predicting it's not actually predicting the tokens of the prompt, but that is still part of its training data. What it is predicting is the completion. So it's going to predict like maybe the word Paris, and during generation, that gets fed in as the input at the next time step, and then it predicts end of sequence. So in most applications, the language model is going to complete a sentence rather than generate something from scratch, and the prefix that is provided, that's the prompt, and then the completion is the desired output. Okay. So we're going to say that maybe a basic formulation is that the completion is our action. So A is represented by the two tokens Paris and end of sequence. And in general, this could be a variable number of tokens. And the prompt or prefix or context is the state S. So our language model is representing P of A given S. Now the way it's representing it is by a product of probabilities at every time step. Since it's not generating x1, x2, and x3, and x4, that's the prompt, it's only generating x5 and x6. So the probability of A given S is given by the probability of x5 given x1 through 4, and the probability of x6 given x1 through 5. And I've separated x1 through 4 from x5 because x5 is really the previous time step of the action, whereas x1 through 4 is the state. So pi of A given S is essentially our policy pi theta. Now, something to note here is that there are now two notions of time step, and this is actually super confusing. The time step x1, 1, 2, 3, 4, 5, 6, those are the time steps for the language generation for the transformer. As far as the RL algorithm is concerned, there's only one time step. You observe one state and you create one action. So this is confusing because now in regular RL, time step always meant the same thing. Now there's actually two kinds of time steps. There's the language time step, and then there's the RL time step, and they are not necessarily the same. So for RL purposes, there's really only one time step here. It is a bandit problem. It is a one-step MDP. As far as language generation is concerned, there are many time steps. Okay, so now we've defined time steps, we've defined actions, we've defined states, and we've defined our policy. Our policy probability is represented by a product of the probabilities of the language time steps for all of the completion steps. Now we can define our objective, which is to maximize the expected reward under the policy, just like in regular RL. And this makes it a basic one-step RL problem that is a bandit. Okay, so let's start with using the simplest RL algorithms, which is policy gradient. So this is our objective. We're going to take its gradient, and we'll use exactly the formulas from the policy gradient lecture. So we know that the gradient of the expected reward is the expectation of grad log pi times r. Now, we saw before that pi was just a product of the probability of all the tokens in the completion. So when we take the gradient of the log of pi, that's just the sum of the gradients of the log probabilities of all the completion tokens. Okay, so that's pretty straightforward because these are exactly the kinds of gradients that you compute when you do a backward pass from the cross-entropy loss. And of course, we can estimate this with samples. So if we use a standard reinforce estimator, then the samples need to come from pi theta. So you would actually sample a completion from your language model. You would actually tell it what is the capital of France, ask it to generate a completion. It would generate Paris end of sequence, and then you would evaluate the reward of that sample and use that as part of your gradient estimator. You can also use an importance sampled estimator, where you might generate completions from some other policy and then use an importance weight to get a gradient for your current policy. And the samples can come from some other policy, pi bar, PyBar could, for example, be a supervised training model. The first estimator is a reinforced style estimator. The second one is an importance weighted estimator, such as PPO. The second class is a lot more popular for language models. You can take a moment to think about why that is. So the reason why the importance weighted estimators are much more popular for language models is that sampling from a language model takes considerable time. And it would be very desirable not to have to generate a sample every single time we take a gradient step. Especially because evaluating the rewards of those samples can be expensive, and we'll talk about that in a second. So in reality, it's often much preferred to generate samples from your language model, evaluate the rewards of those samples, and then take many gradient steps using importance sampled estimators, and then repeat. Okay. So a particular algorithm, let's take this importance sampled estimator, let's call it grad hat as a shorthand, and notice that it's a function of theta, pi bar, and a set of samples, AI. The way that you could do this is you could sample a batch of completions for a particular state. In reality, you would have many states, but I've written this out for just a single state. You would sample a batch of completions. You would evaluate the reward for each of them. Then you would set pi bar to be your previous policy, the one that generated those samples. And then you would have an inner loop where you would sample a mini batch and then on that mini batch, you would take a gradient step using grad hat. And then you would repeat this k times. So your batch might be, let's say, 1,000 completions, and then your mini batch might be 64. And then you would take some number of gradient steps, and then every once in a while, you'd go back out and generate more samples from your model, set that to pi bar, and repeat. So this is very much the classic importance sample policy gradient, or PPO style loop. And this is a very popular way to train language models with RL. But one big question with this loop is the reward. So notice that every time we generate a batch of completions from a language model policy, we have to evaluate the reward of each of those completions. Where do we get that? Because typically, if we were to train on, let's say, question answering questions like what is the capital of France, we might have a ground truth data set of answers. But here, the policy might generate answers that are not in that data set. So we need it to have a reward function, and that reward function needs to be able to score any possible completion for a given question. So very often when we do this, we want to represent R itself as a neural network. Because we don't just have to figure out that Paris is the right answer and should get a reward, let's say, +1. We also have to figure out what happens when the language model says, oh, it's a city called Paris. Well, that's a pretty good answer, like it's correct. It's maybe not as concise, so maybe we give it a slightly lower reward. Maybe we say that, oh, that's a 0.9, not a 1.0. It might also say, I don't know. That might not actually be incorrect, like maybe it really doesn't know, but that's a worse answer, so maybe we give it a negative 0.1 or something. And then if it says London, well, that's just bad. That should be a -1. But it's a language model, so it can really say anything. It might also say like, oh, why are you asking such a stupid question? So that maybe is extremely undesirable, and we give that like a -10 to get the network to behave itself. So your reward model doesn't just need to know what the right answer is, it needs to also be able to understand how to assign rewards to answers that are only a little bit off, or answers that are extremely different, kind of out of scope of a question. So this is a very kind of open vocabulary kind of problem, so you need actually a very powerful reward model. So what could we do? We could take all these potential answers, we might sample them from some language model, maybe we have a supervised training language model to get started, we sample some answers and we give them to humans, and we get humans to generate these numbers. So maybe humans look at these answers, they assign numbers to all of them, that creates a data set consisting of sentences, like what is the capital of France, Paris, what is the capital of France, stupid question, where the label is the number, and then we take supervised learning and we train a model that basically looks at the sentence and then outputs this number. And that could be a way to train a reward model, our psi. I'm going to use a subscript psi now to denote the parameters of this reward model. But then, of course, the problem is, how do people know these numbers? How can people actually assign the number -10 to why is this such a stupid question? Maybe some people can do this. Maybe you can actually, in some settings, have a task where there are clear units of correctness. Maybe perhaps it's a teaching application, and the reward is how correctly the student answered the test. Or maybe it's some salesman application where the reward is how much revenue did you make. So in those cases, maybe the rewards are very quantitative and people can actually label that. But in cases where it's very subjective, like saying that why is this such a stupid question should be a -10, whereas London should be a -1. In those cases, maybe it's hard for humans to assign clear numerical values to these things. What might be easier for humans is to compare two answers. So if you tell a person the question was, what is the capital of France? And you have A and B. A is Paris, B is why is it such a stupid question? It's pretty easy for a person to say, oh, I prefer A. So a preference might be in some cases easier to express, especially when the utility is very subjective. So here's a thought. Can we use these kinds of preferences to design reward functions? Now, reward functions have to assign a number to a particular answer. Preferences are a function of two answers. So given S, A1, and A2, how likely is a person to prefer A1 over A2? That is a well-defined probability. So if the state is what is the capital of France, the actions are Paris and why is such a stupid question, the preference A is the label, we could simply model the probability that A1 is preferred over A2, and we can learn that. But since what we want in the end is a reward function, what we can do is not actually train a neural network that predicts whether A1 is preferred over A2, but we can describe this probability as a function of reward. And there's a choice that we have to make here. So one very popular choice that is actually derived from the same mathematical foundations as maximum entropy inverse RL that we discussed in the IRL lecture, is to model the probability that A1 is preferred over A2 as the exponential of the reward of A1 divided by the exponential of the reward of A1 plus the reward of A2. So roughly speaking, this means that the probability that A1 is preferred over A2 is proportional to the exponential of its reward, which means that if one reward is clearly better than the other, then that one will definitely be preferred, but if their rewards are about equal, then they're about equally likely to be preferred. And the reason for the exponential transformation mathematically is very similar to what we saw in the Maxent IRL lectures. I won't go into the math of that, but that's basically the intuition. So now the way that we can actually train this is we just maximize the likelihood of the preferences expressed by the human on these S, A1, A2 tuples, but where the predictor for that preference is parameterized by our psi using this ratio at the bottom of the slide. And then we just take the logarithm of that and we maximize the log likelihood with respect to psi. And that's a well-defined supervised learning problem. So that's a way that we can get numerical rewards out of pairwise preferences. And you can, by the way, extend this pretty easily to cases where the preference is expressed over more than two items. So you can show the person 4 completions and get them to say which one they prefer. In that case, you'll have 4 values in the sum and the denominator. You could also take 4-way comparisons and turn them into all possible pairwise comparisons. And that's also another way that you could express this. So you could say, well, if you show someone A1, A2, A3, A4, and they prefer A1, then you say A1 is better than A2, A1 is better than A3, A1 is better than A4, and turn that into 3 pairwise comparisons. That's also valid. So here's an overall method that we can use with this scheme, and this method was described in 2 papers, Fine-Tuning Language Models from Human Preferences and Training Language Models to Follow Instructions with Human Feedback. These basically are the foundation of InstructGPT, ChatGPT, and so on. The overall method is to first run supervised training, or typically fine-tuning, to get your initial policy pi theta. And that's just supervised training of a language model. And then for each question in your data set, for each S, you would sample k possible answers, AK, from your policy, and construct a data set consisting of tuples with a prompt SI and k possible answers, AI1 through AIK, for that prompt. Then you would get humans to label each of those points, each of those S, A1 through AK tuples, to indicate which answer they prefer. And then you would use that labeled data set to train R-psi. And then you would update pi theta using RL with R-psi as the reward. And then you would repeat this process some number of times. Now, typically when you do this, in step 5, you would actually run many steps of policy optimization. So in step 5, you wouldn't just optimize against that reward once with import sampling. You would actually generate samples from pi theta, optimize, generate more samples, and repeat. So there's actually 2 nested loops here. There's the outer loop where you're generating more samples and asking humans to express preferences. Then there is another loop where you're actually running this policy gradient, and inside that there's another loop where you're running important sampled updates for multiple steps. So that's the overall method. Now, there are some challenges that we have to take care of. First, human preferences are very expensive. because that actually involves like sending a bunch of data out to human labelers. It might take days or even weeks to get responses out. Of course, if you have a really nice crowdsourcing system, perhaps you'll actually get answers back within hours, but it's still way slower than taking gradient steps on a GPU. So you want to minimize how often you send things out for human labeling. So in practice, most preference data typically actually comes from the initial supervised trained model. So even though I wrote this as though it were a loop where you repeatedly query more preferences, in reality, the first time you go to step 2, you label lots of preferences. And then on subsequent tries, you have significantly less. In fact, if you want the poor man's version of this, you might actually not even have that outer loop. You might just do steps 1, 2, 3, 4, 5 once. So human preferences are expensive. You also want to take many iterations of RL, including generating new samples from the policy, per each iteration of preference gathering. And that actually makes this very much like a model-based RL method. So since this is a one-step problem, there's no dynamics model, but there is a reward model. That reward model is trained much less frequently, and then many RL updates are made on the same reward model. In fact, if you don't have that outer loop and you just do steps 1, 2, 3, 4, 5 only once, it's actually an offline model-based RL method. So what's the problem with that? Why should we be worried? Well, the problem, of course, is what we saw before in the model-based RL discussion. The problem is distributional shift. And in RL for language models, that is sometimes referred to as over-optimization, which basically means that you exploit the reward model after a while, and while the policy initially gets better, later on it gets worse. The other problem is that the reward model needs to be very good. So over-optimization is often tackled with a simple modification, where we simply add a penalty to our expected reward objective that penalizes the policy pi theta from deviating from the original supervised policy. And this KL divergence can conveniently be written by just adding log probabilities from the original supervised trained model to the reward, and then subtracting the log probabilities of the current model, which is just an entropy term. So this just changes the reward function. You take your reward model, and then you add the log probabilities of your original supervised trained model, and subtract the log probabilities of your current model. And beta is just a coefficient. And typically when you do this, you would use a very large reward model, typically a large transformer that is itself pre-trained to be a language model, and then fine-tuned to output the reward. Because the reward model needs to be very good. It needs to be powerful enough that it can resist all that optimization exploitation pressure from reinforcement learning. Okay, so to recap an overview, we can train language models with policy gradients. We typically use importance sampling estimators. It's a bandit problem for now, although we will make it multi-step in the next section. We can use a reward model, which can be trained from human data. And typically we would actually train it with preferences rather than utility labels, using this equation as the probability that the user prefers A1 over A2. And this can be more convenient than direct supervision of reward values. Now, all of this technically ends up being a model-based RL algorithm because we train the reward as essentially a model, and then we optimize for many RL steps against that model. It could potentially be an offline model-based RL algorithm if we actually don't get additional samples from a policy and send them out for more labeling. There are details to take care of, such as minimizing human labeling and over-optimization, and we should use a large reward model that is very powerful so that it can handle that setting. And the way that we address over-optimization is typically by adding this little KL divergence penalty to ensure that the policy doesn't deviate too much from the supervised trained model.